Okay, so this is going to sort of start off our uh, discussion of positional controls. If you remember from your symbols, we have three positional controls. We have symmetry, or we have location, symmetry, and concentricity. These, of course, are special cases of position. Symmetry is a condition where a feature is halfway between two other features. Concentricity means that two features share the same derived median element, usually a center line. But both of these cases are specialized and they can be controlled by positional control. I see very much less of these two in current drawings, so I think people are generally tending towards the position symbol. All right, so what I'm going to direct you to is figure 7.2 in the handout. I've handed out, or added up, loaded up about half of the chapter on position. Position is far and away the most common control, far and away the most complex control, and you can do a tremendous amount with it. We're not going to get through very much of it at all. I just want to introduce to you some of the concepts and sort of make a distinction why we have a separate control for position as opposed to form and orientation. Now you've already seen that when we use orientation controls, since orientation controls control only rotational degrees of freedom, we use location controls to take care of the translational aspects. But don't ever forget that you can use those in conjunction. If you don't, then whatever tolerance zone you put up there defines all those aspects. So it's often a desirable thing to use these things in conjunction with each other. And this is a good example of it here. You're going to see where we take care of positional control, we take care of orientation control, and I'm going to add to this illustration, I wish they had, a form control. All right, so what you see here is a ring, a fairly thick ring. It has 6 holes. Each one of those holes is defined, or the derived median element of those holes is defined by a basic dimension. If you remember, basic means that there is no tolerance attached to that dimension. The tolerance is expressed elsewhere. The options to identify a basic dimension are they'll either be in a box or there'll be a note saying that untoleranced dimensions are basic. In this case, that's what they've done, and I think it's a good thing because I've only drawn a couple of the dimensions here. There are a lot of dimensions locating 6 holes. So there's a total of 12 location dimensions, and that just starts to get pretty cluttery. So in this case, if it doesn't have a tolerance on the dimension, it is basic according to the note in the bottom of the view. So all of these basic dimensions are defining perfect geometry. They want you to establish a framework of perfect locations, 6.64 and 10 millimeters from the center line of that hole. Okay, so can we make them perfect like that? No, but that is going to be our basis from which we draw the tolerance zone and evaluate where they are relative to that perfect geometry. So let's start out with the datums, since we do have some datums here. The first datum is the bottom surface of this ring. It is identified as datum A. Now, realistically, if you're going to go down this route, and this is a perfectly legitimate way of doing this, very often there would be a form control for that primary datum. In other words, datum A is a flat plane. How flat? Well, we don't know here. We don't know what control is on that plane. So it's always a good idea to define some sort of tolerance on that flatness. I'm going to say 1/1000 of an inch. That's nice and flat. That's a good starting point, and that is the primary datum. So if I have this ring, datum A is a plane, 3 points. If I set that ring on those 3 points, I have now constrained this ring from certain translations and certain rotations. I can still translate fore and aft, side to side, but I cannot translate in Z, so I can't come off those 3 points. So I've constrained one translational degree of freedom, and I still have 2 translational degrees free to me. Rotations, I can rotate about Z, so I still have that one. I cannot rotate in pitch. I cannot rotate in roll. So I've locked out 2 rotational degrees of freedom simply by establishing this primary datum A. The secondary datum is identified here as datum B. It is attached to the feature control frame defining that feature. That's perfectly legitimate. And that means that we are now constrained not only to datum A, but we are constrained to the center line of this pin. So with the establishment of datum B, where before I could translate this way and this way, if I have to stay fixed to the derived median element of B, I can no longer translate this way or this way because I have moved away from that datum. I can still rotate. I still have this one rotational degree of freedom available to me. That means that this part is not fully constrained, but if you'll think about it for a second, do I really need to constrain this rotational degree of freedom? So if you think about it, if I'm going to come down with a drill head and drill all 6 of these holes in a pattern, does it matter whether this part is rotated this way or that way? It really doesn't. So I don't need to constrain that rotational degree of freedom. There are ways to constrain it so it is fully constrained, but right now this part is not fully constrained. There is still one rotational degree of freedom. Okay, so now let's look at the feature that we're actually controlling, which is these 6 holes. And they're defined, and there's 6 of them, and they are diameter 3.32 and 3.30, metric of course, and there is a positional control. Now again, almost everybody says true position. That isn't the terminology they use, but everybody will call us a true position symbol. It is actually a locational control locating position. Alright, so now I'm going to define the tolerance zone. I know it's a diametral tolerance zone. It is 0.3 millimeters in diameter, about 30 thousandths. At maximum material condition. And I have datum A and I have datum B. And there's a material condition modifier in datum B. So, well, we haven't really dealt with that yet. Let's see what that really means. We know that the material condition modifier adjusts the tolerance zone. It always adjusts it upward from where it is at maximum material condition. Alright, so let's take this apart. We are going to look at this tolerance zone for each one of these individual holes. Each one of them gets this tolerance. So right now we're going to consider just this one hole, and we're going to look at, real close up again, the tolerance zone, and I'll draw it as 0.3 diameter. Circle. And that circle, of course, is right here. It's just the tiniest little circle around the actual center line that's located at 10 and 6.64. And that means that the actual whole center line can be anywhere within that circle and be acceptable. It's a uniform tolerance zone. That's all well and good. Okay, so now let's look at what this material condition modifier means. We know that in the case of the material condition modifier in the tolerance zone block, we look at this hole, this feature. It is a feature of size. It has a tolerance of 3.32 to 3.30, so 0.02 allowance. This now means that if this feature, if this hole is at maximum material condition, which if you'll remember is the smallest hole. So if we drill that hole exactly at 3.30, we get a tolerance zone of 0.03. If we drill it up to 3.31, we get to add 0.01 to that tolerance zone, and it now becomes 3.01. If we drill it all the way up to the least material condition, here, we'll add another 0.01, and the tolerance zone at least material condition becomes 3.02. So the material condition modifier tells you that at maximum material condition, this tolerance zone is what is written there, 0.3. If you need or want more tolerance, you start drilling that hole up a little bit bigger. Now you can't go too far, 0.01, 0.02 millimeters, those are pretty small amounts, but it is tolerance and we can add it, and at least material condition that tolerance can be 3.02. Now let's look at datum A. Datum A is a plane. It has no thickness. We can't really evaluate its size because it's an intrinsic control. So there's no way to put a material condition modifier on A, but on B, it is a hole. It has a tolerance of 0.2 millimeters, a bigger tolerance. And we're saying that we can adjust the tolerance zone based on the size of that datum feature too. So not only do you have the tolerance zone being adjusted based on the size of this feature, we also can adjust the tolerance zone based on the size of this feature. Okay, so let's start back at 0. The feature control frame says when the feature is at 0.3, or when the feature is at maximum material condition, when it is its smallest, and when the datum feature is at maximum material condition, when it is at its smallest, this is the tolerance zone you get. Maximum material condition of the feature, maximum material condition of the datum, you get no additional tolerance. If you start drilling this up and you make that hole at 3.32, we ended up with 3.02 diameter tolerance zone. But we're not done. We can get more, and if we start out with this datum feature at 18.8 at its smallest, if we drill it up 1/10 of a millimeter, let's say that hole then becomes 18.9, we'll add that 0.1 to this and we'll end up with 3.12. And we're still not done. If we take the datum feature up to least material condition, maximum material condition, we'll get an additional plus 0.1, and that tolerance zone then becomes 3.22. So we've gained almost an extra quarter of a millimeter tolerance just by going from least material condition, or maximum material condition to least material condition on the feature and on the datum. Okay, it isn't always obvious why you do that. From a designer's point of view, it is a practical way to design gauging so we don't have to measure those features each time. We can actually make a physical gauge that we can slide the part on. And that's why this is very useful, the maximum material condition modifiers on the feature and on the datum. The bottom line is, from your point of view, you want to know how much tolerance you get. In order to figure out exactly how much tolerance you get, you have to measure that specific hole and that hole and see where they are between maximum material condition and least material condition. If they're both at maximum material condition, that's all you get. If one of them starts deviating from maximum material condition and heading towards least, you get to add that tolerance, that difference, you add right to the tolerance on a thousandth for a thousandth basis. In other words, make the hole a thousandth bigger, the tolerance zone gets a thousandth bigger. Not only for the feature itself, but for the datum. Okay, now let's say you've evaluated that hole and you've figured out what your tolerance zone is for that hole. You have to go back through it and do it again for each one of those other 5 holes, because each one's going to be a little bit different. Each one will be a little bit different in size, and accordingly the tolerance zone will be different for each one of those. Okay, so that's a lot to swallow. I'm not going to talk any more on this video about this. I want you to be thinking about this and how these datum and feature modifiers can allow your tolerance zone to get bigger and bigger. And of course, the beauty of this is that if you can control the size of these holes, you can determine how much tolerance you get within the range of the size of the features. I do want to talk about, I'm going to erase some of this here. I do want to talk about this feature control frame on datum B. Kind of blow it up here. It is an orientation control. So it must have a datum, and it does. It's datum A. And it has a size. It is diameter 0 at maximum material condition. Okay, now we talked about this briefly on another video, that you'll know that you'll always have some tolerance. You'll never get 0 tolerance, but here it's telling you that you get 0 tolerance. But it's 0 tolerance at maximum material condition. In other words, when this datum feature B is at its smallest, this hole, or the center line of this hole, has to be perpendicular to A within 0. It has to be perfectly perpendicular, perfectly square to surface A. So here's surface A. Here, well, let me use my ring. Here's surface A. That datum axis has to be perfectly perpendicular to it. In order to get additional tolerance, I have to adjust the size of datum surface A, open it up a little bit, and now that axis can tip a little bit more. Okay, so a lot of things are happening here. A lot of things are happening all at once. The tolerance zone for the size of these holes, or the location of these holes, is adjustable both by the feature size and the datum size. The orientation of this hole is adjustable based on its size. So this is a constantly shifting set of requirements that you have to evaluate each time you pick up a part. That seems like it's a lot of extra work, and if you're doing it, you know, by measuring, if you're measuring size each time and you're measuring orientation each time, it is a lot of extra work. And the beauty of it is that I can now design a fixture that no matter what size these features are, I can make it so you don't have to measure the size or the location. The gauge will do all of that automatically, and as long as I can slip that part onto a pin, and on a pin here, or on all 6 of those pins, I can, in one drop of that part, if it goes on the pins, it's acceptable. It is within the tolerance zones. So that is the real rationale for GD&T, is to be able to eliminate all this physical measurement of size and orientation. We can design now a gauge that will do that without any of that measurement. All right, I know that's hard to absorb right now. I want you to think about this stuff. I want you to think about the notion of starting out with a primary datum that you have a form control on, so it's nice and flat. Because if this datum were curved like this, or wobbly like that, that wouldn't be a good starting point for the perpendicularity of that feature, would it? In other words, A could wobble out all over the place. How would you evaluate the perpendicularity? So we start out with a form control on the primary datum. The secondary datum now has an orientation control to the primary datum, and we can adjust that tolerance zone based on the size of both the feature and the datum feature. All right, that's enough. Think about that a little bit. We'll move on to some of the more sophisticated controls, but I think figure 7.2 is one of the very best examples in this book that shows you exactly how it's meant to work. What they don't show you, and I wish they would, is that what the means this is. What this means is that we have 6 independent tolerance zones. Each one of them is 0.3 in diameter when each one of these holes is at its maximum material condition, when it's smallest. Each one of them can be adjusted based on the size of that hole, and it can also be adjusted based on the size of the datum hole. Let's leave it at that. I'll be back in touch by email with you here about the middle of the week to talk about the grading election. I'm sure it's going to be confusing. I'm a little bit confused myself, but ultimately you're going to have to make a decision whether you want a pass-fail reported to the school or whether you want your letter grade.